Hey folks, welcome to another lesson and another application of specific latent heat calculations. So there's a wee bit extra here because we're going to tail back to look at space and particularly about the problems that you have on re-entry from space into the Earth's atmosphere. And that's where these calculations are going to be based on. So there's a wee bit of revision about specific latent heat and specific heat capacity as well. So first of all, I've set up this assignment for you to do, which is about re-entry from space. It's 2 videos to watch and a total of 4 questions per video. It's fairly straightforward. It's just to give you an idea of some of the problems and solutions we have for re-entry and entry into space. Really make sure you watch those and get an idea of it because they do tend to come up quite a lot in tests and assessments. So first of all, I'd like you to write this down. There will be a fair bit of writing because we're going to be doing quite a number of practice and worked examples. So first of all, when a satellite re-enters Earth, it has to convert its kinetic energy to heat energy. That's really how it slows down. And that's true for any moving object. Remember, a moving object has kinetic energy. And by conservation of energy, you can't destroy that energy, you can only transform it to another form. So to get rid of that kinetic energy, you usually change it into heat energy. And because in space you're dealing with really fast speeds, as you'll know from watching the video, then we're talking about huge amounts of kinetic energy being converted to heat energy. And so this is another application of specific and latent heat as well. So a wee bit of revision for you. What are we going to need to use? We're going to have to use EK is equal to half mv squared. And the idea that conservation of energy means that the kinetic energy is equal to the heat energy because EK is transformed into EH. Second one, EH is equal to Cm delta T. Remember, conservation of energy means that EK is equal to EH. So if you know what the kinetic energy is, you know what the heat energy is. And so you may be asked to calculate the mass, the change in temperature, or the specific heat. And remember, you only use this equation if there's a change in temperature. And that's why you have this delta T here. EH is ml. Use this if there's a phase change, i.e. a change in state, or when there's no change in temperature. Okay, and again, I know some people got confused with this last time, but remember, this one here, specific heat, there's a change in temperature. Latent heat, there's no change in temperature. And that's how you spot which one you use. The final thing is with EH equal to ml, remember this is a latent heat and there's 2 versions you can use, latent heat of fusion or latent heat of vaporization, and you have to choose which one. Fusion is when it's going from a solid to a liquid or a liquid to a solid. Vaporization is when it's going from a liquid to a gas or a gas to a liquid. And then finally, you may be asked to work out a work done is equal to FD. And remember, conservation of energy, EW is equal to EH is equal to EK. So friction creates heat energy. So this is where this equation comes in. So a lot of things to remember here and a lot of things to kind of keep in your mind. But this is a really good lesson on revision and to show you how all the physics can really combine together to give you new physics or allow you to solve what can be quite complicated problems. Okay, so let's get straight into the examples now. Feel free to pause the video at any point and try the questions yourself. I really recommend that because even if you get it wrong, you can at least see where you've gone wrong. And if you get it correct, absolutely brilliant. So, small satellite of mass 2 kilogram falls, re-enters the Earth's atmosphere at a velocity of 3,000 meters per second. How much heat is produced? So, pause the video, try it yourself. Now, hopefully, even if you don't know what to do, you should be doing your KFC technique. So we know we're going to use kinetic energy, and it's going to be conservation of kinetic energy to EH. This is a wee bit later on, but this is what I'd expect to do. M is equal to 2 kg, V is equal to 3,000 meters per second. Check that in the correct units. And from there, I would hope, because that's the only information you're given, you'd be thinking kinetic energy. So that's why I've got this here. So we write down an equation. EK is equal to half mv squared. EK, you substitute in your values, a half times 2 times 3,000 squared. And remember, it is only the 3,000 that is squared, not the whole thing. And then the final answer would be whatever we get for our EK, that must be the heat energy. So the answer there is EK is equal to 9 million joules. So EH is also equal to 9 million joules. So I'd expect you to write a final line, EH is equal to 9 million joules, which is this one here. Okay, and that's how you do this example here. So notice it doesn't tell you to calculate the kinetic energy. You have to figure that out yourself. But by now, I would hope if you're doing the KFC technique, this makes it obvious you're using EK and then using conservation of kinetic energy is equal to EH. Okay, so let's look at a different example here. And again, feel free to pause the video and try it yourself. I will take you through the solution on how to solve this. So it says a solid meteorite of mass 20 kilograms and made entirely of aluminium enters the Earth atmosphere. It changes from a solid to a liquid at 1500 degrees Celsius. Calculate the heat energy of the meteorite as it enters the atmosphere. So even if you don't know what to do, the minimum I'd expect to do from the KFC technique is know it. So that means find the information from the question. So you've got mass is 20 kilograms, temperature is 1500 degrees Celsius, and we know we're looking for the heat energy. Now, the trick to this question is, do we calculate the heat energy using a specific heat capacity, EH is equal to Cm delta T, or is it latent heat? Well, there's two bits of information that helps us decide which one it is. So let's read the question again carefully and see what it says. And I'm going to focus on this sentence here. It says, it changes from a solid to a liquid at 1500 degrees Celsius. So I would hope it's obvious to you if it's changing from a solid to a liquid, there's a change in state or a change in phase. So that means it must be a latent heat. The second bit of information that's important is that it says at 1500 degrees Celsius. So notice I've only put this as 1500 degrees Celsius. I've not put this as delta T. Delta T means there's a change in temperature. There's no change in temperature here as it stays at 1500 degrees Celsius. Now, the other bit of information that's important is that if it's going from a solid to a liquid, it tells us we're using the latent heat of fusion. So you can look this up in the data book, and remember it's the latent heat of fusion for aluminium because that's the material that's changing state. Once we've got that, we're on easy street because we just find the equation. We know it's EH is equal to ml. We plug in our numbers and then we calculate the answer and we get this as our final answer. I would leave my answer like this. I wouldn't bother convert it into standard form. Don't give yourself extra work if it's not asked for it in standard form. And remember, no change in temperature, use the latent heat. You can tell which one it is, latent heat of fusion or latent heat of vaporization, by what the change in state is. Solid to liquid or liquid to solid, it's a fusion. Liquid to a gas, gas to liquid, it's vaporization. Okay, this is the final example, and this says the nose section of the shuttle is covered with 350 kilograms of heat-resistant tiles. During re-entry, they experience a rise in temperature of 2000 degrees Celsius during the shuttle's journey back through the Earth's atmosphere. The shuttle is slowed from 2000 meters per second to 150 meters per second during this part of the journey, and there are 3 questions to answer. So again, pause the video, have a go at this yourself. I'm going to take you through each one over the next couple of slides. Okay, let's look at how we do the first one. So again, we're using our KFC technique. So we've got mass is 250 kilograms. Now notice it's a change in temperature because it says it experiences a rise in temperature of 2000 degrees Celsius. If the temperature is rising, then it must have been changing. So that's why I've got it as delta T. Now I've called these U and V, so I know which one's the initial and the final speed. Now, hopefully you know it's kinetic energy, so you know it's EK is half mv squared. We have to calculate each one separately. So we have the first one, and we've got 7 times 10 to the 8 joules. Do the same for the second one, and we get this number here. Now, a wee point. I know a lot of you would by now hopefully round this number up. Because this is only the middle of a calculation, you're going to be using these values for the next bit. I wouldn't bother to round it up. You only ever round when you're doing your final answer. So to get the kinetic energy loss, we do the initial kinetic energy minus the final kinetic energy, and this is how much energy has been lost. And you can, of course, round this answer up. I've not rounded this one up, but you can round this one up. So that's how we do part A. Part B, how much heat energy is produced at the nose during re-entry? Well, this is really a EK equal to EH question answer, isn't it? So we're using conservation of energy, saying that all that lost kinetic energy has been changed to heat energy, so that's why it's the same as the answer in part A. And that's really where the physics is. So make sure you understand that point, that the kinetic energy is being changed to heat energy. Now, onto our final slide here. So, calculate the specific heat capacity of the material used to make the nose tiles. And if you weren't sure already, remember we said there was a rise in temperature. So that means there's a change in temperature. So that backs up this idea that we're doing a specific heat capacity calculation. So we've got the energy. Now, as always, if you're not sure about how to do the final part of a question, for example, here you're thinking, well, I know it's a specific heat capacity, but what's the heat energy? Because it doesn't tell me in the question. Look back on the previous part of the question, because quite often they get to use a previous part of a question in the next part. And then we know it's got a change in temperature at 2000 degrees Celsius. So we write down our equation. Now I've jumped ahead a wee bit, but you can see this is EH is equal to C times M times delta T. And then if you're not sure how to rearrange it, I would multiply out any sums that you can do on either side. So we can do 350 times 2000. That gives us 700,000 times C is equal to the heat energy. And hopefully you can rearrange that. So that would be C is equal to this number divided by 700,000, which gives us this answer. And then we would round it to the nearest whole number, 994 joules per kilogram per degree Celsius. And make sure you have the correct unit for specific capacity. It is a wee bit awkward. If you forget the unit for this, you can look at the data sheet because it is in the data sheet.